Okay, we're going to start into a new topic, and the new topic is going to be moment of inertia. Now, what is moment of inertia? Or what are you going to be required to do in this chapter? What you're going to be required to do is take a shape and calculate its moment of inertia about some axis. Okay? Now again, you might say, well, what axis would you require that for? Well, we just spent some time determining the centroidal axis of a shape. So that the centroidal axis might be a very common axis, either the centroidal x or the centroidal y-axis might be a very common axis to take and calculate moment of inertia about. Okay? So your job is to learn how to take a shape and about some axis, maybe like the centroidal axis, be able to calculate the moment of inertia. Okay? So back when you were talking about centroids, your job was to find the centroid. Here, your job is going to be to calculate moment of inertia. All right? Well, what is moment of inertia? Why do you care about moment of inertia? Well, let's say I had a beam, and I'll hold up sort of this yardstick. All right? And let's say this yardstick represented a beam, and it was supported at both ends, and then you put loads down here along the length of the beam. Now, this is just one yardstick, right? But if you put those beams as it was like this, you would see the beam bend. Okay? And you'd see it bend noticeably. What if you orient it was the same beam, but you just oriented it like this? Now you support it at the same place, you put loads across that beam, and those loads now are on the same beam in the same location, but do you see it deflecting? Well, it is deflecting, but you don't see it deflecting nearly. I mean, to your naked eye, you don't see this deflecting at all. But yet, when I held it like this, you could easily see the deflection that's occurring. But like this, you don't hardly see anything. Why? What's the difference? It's the same piece of wood I was dealing with, right? The only difference is it would seem very strong when I had it oriented like this, and yet when I had it oriented like this, it seemed a lot more flexible. Well, why is it stiffer in one orientation and more flexible in another orientation? The reason is moment of inertia. You're going to find that for that yardstick I was holding up, that it has two axes. All right? Let's call this the x-axis. Let's call this the y-axis. You're going to find out that when you bend it about the x-axis, that the x-axis moment of inertia, the moment of inertia about the x-axis, is much, much larger than the moment of inertia about the y-axis. So when the moment of inertia is large moment of inertia, and we represent moment of inertia with I, the letter I. When we have a large I, that means more bending resistance. More resistance to bending. It's stiffer when you try to bend it. A smaller I correspondingly means lower bending resistance. It seems more easy, more flexible to bend. All right? So when I was orienting this yardstick like this, it was pretty stiff. But when I orient it like this, you could see the deflection. Okay? So, this axis here, the moment of inertia about that axis must be much smaller than the moment of inertia about the other axis. That's what you're going to learn to calculate. Okay? So, where we start out here? Well, we can start out here, again, pretty much like we did with centroids. And in centroids, we said, hey, there's a table. It's got the location of the centroids for standard shapes. Well, in your book, if you go to page 218, there's another table that gives you the moment of inertia for standard shapes about the standard shape centroidal axis. So on page 218, you have another standard shapes type table, and those standard shapes give you little formulas to calculate the moment of inertia about those shapes centroidal axis. Now, isn't that sort of nice, because we just got done learning about centroids, and here now we're calculating some property of area relative to those axes, those centroidal axes. So you can see the rectangle there up top. That's a very common shape. The moment of inertia is bh cubed divided by 12, where b, you can see, is the base. Triangle, bh cubed divided by 36. And then you got the circle and the semicircle, which are a little bit less common, but still you have the formula there in front of you. So, again, standard shapes. What can you tell? Let's just throw some numbers on here. Okay? Like, let's play around with our yardstick. Let's say our yardstick was 1 inch by, let's say this was a 1/4 inch. Let me erase this. Okay? So I oriented it like this. It was very strong when I tried to bend it about this axis. Okay, so let's say it was 1 inch overall measurement here and a 1/4 inch width. By our standard shape formula, my moment of inertia would be base 1/4 inch times 1 inch cubed divided by 12. Okay? Now that's not going to seem like a big number, but that doesn't bother me too much. What is a 1/4 inch divided by 12 times 1 cubed divided by 12? What does that come out to be? 0.25 divided by 12. .02. Okay. So again, the units on that would be inches to the fourth, but that's not anything that you need to get too concerned about. Let's say what would happen when I oriented the yardstick like this? I still have my 1 inch side, right? Still have my 1/4 inch side. It was the same piece. It was the same yardstick, right? What's my moment of inertia when I do this? Well, what's the base now? 1 inch. What's the height? 1/4 inch. I got to cube that 1/4 inch. Now I got to divide it by 12. So take 0.251 times 0.25 raised to the 3rd power divided by 12. What's that value? Just take 0.25 times 0.25 times 0.25 divided by 12. Yell it out.
0.0013.
Now again, that's inches before. Now again, that's a real small number, but do this for me. take 0.0208, which was the moment of inertia S, divided by 0.0013. What do you get? What was it? 16? What that's saying is this first orientation of my beam, my yardstick here, is 16 times stiffer, more resistant to bending, because it had a 16 times larger moment of inertia about that axis.